James Webb's early galaxy discoveries and did the universe grow up faster than expected is a question that is currently rewriting our entire understanding of cosmic dawn. Deep in the infrared shadows of the early universe, the James Webb Space Telescope has captured images of massive mature galaxies that simply should not exist yet. These universe breakers appear fully formed a mere 500 million years after the Big Bang, defying every model of stellar evolution we have ever built. If these observations hold true, we are not just looking at new stars. We are looking at a timeline that is fundamentally broken. Somewhere in the vast stretch between the first spark of light and the modern day, the universe found a way to grow up in an impossible hurry, and scientists are still trying to understand why. To understand why these discoveries are so shocking, we need to go back to the very beginning. Not the beginning of astronomy or the beginning of science, the beginning of everything. The moment when the universe itself switched on. Roughly 13.8 billion years ago, something happened that we still cannot fully explain. All the matter, all the energy, all the space and time that would ever exist erupted from a single point of unimaginable density and temperature. This event, the Big Bang, was not an explosion in the way we normally think of explosions. There was no empty space for it to explode into. Space itself was being created in the process. Time itself began at that moment. Before the Big Bang, there was no before, because before requires time, and time did not yet exist. In the first fraction of a second, the universe expanded at a rate that defies human comprehension. It went from something smaller than an atom to something larger than a galaxy in less time than it takes light to cross a single proton. This period of explosive growth is called inflation, and while we have strong evidence that it happened, we still do not understand the mechanism that caused it or why it stopped when it did. It is one of the deepest unsolved problems in all of physics. After inflation ended, the universe was a seething ocean of energy. There were no atoms, no molecules, no stars or planets or anything that we would recognize as structure. Just an incredibly hot, dense soup of fundamental particles and radiation all mixed together in a state of perfect chaos. Photons of light were constantly being absorbed and re-emitted by the charged particles in this plasma. Light could not travel in a straight line for more than a tiny fraction of a second before being scattered in a random direction. The universe was opaque. If you could somehow transport yourself back to this era and open your eyes, you would see nothing. Not darkness exactly, just a uniform blazing glow in every direction with no features, no depth, and no way to see more than a microscopic distance in any direction. This state persisted for roughly 38,000 years. That might sound like a long time from a human perspective, but in cosmic terms, it is an eye blink. During those 38,000 years, the universe was expanding and cooling. The temperature dropped from trillions of degrees to merely thousands of degrees. And then something happened that changed everything. The universe cooled enough for electrons to be captured by protons and form neutral hydrogen atoms. This event is called recombination, and it was one of the most important transitions in the history of the cosmos. When the electrons were bound into atoms, they could no longer scatter photons the way they had been doing for hundreds of thousands of years. Suddenly, light was free. It could travel in straight lines across the universe without being absorbed or redirected. The universe went from opaque to transparent in what was, cosmologically speaking, an instant. The light that was released during recombination has been traveling through space ever since, stretching as the universe expands, cooling from a white-hot glow to a faint microwave whisper. We detect it today as the cosmic microwave background, a faint hum of radiation that fills every cubic centimeter of space and represents the oldest light in the universe. But here is the thing that matters for our story. After recombination, the universe was transparent, but it was also dark. There were no stars. There were no galaxies. There was nothing to produce new light. The photons from recombination were streaming through space, but they were gradually losing energy as the universe expanded, and there was nothing to replace them. The universe had entered a period that astronomers call the Dark Ages, and it is one of the most mysterious chapters in cosmic history. The Dark Ages lasted for roughly 100 to 200 million years. During this time, the universe was filled with hydrogen gas, a small amount of helium, and traces of lithium. That was it. No heavier elements existed, because heavier elements can only be forged in the cores of stars, and there were no stars yet. The universe was a vast, cold, featureless expanse of gas slowly being pulled together by the invisible hand of gravity. If you could travel back to the Dark Ages and hover in any random location in the universe, you would experience absolute darkness. Not the darkness of a moonless night on Earth, where there is still starlight and atmospheric glow, and the faint light of distant galaxies. True darkness. Total darkness. The kind of darkness that has no photons in it at all in the visible spectrum. The only light in the universe was the fading glow of the cosmic microwave background, which by this time had cooled to the point where it was invisible to any hypothetical human eye. The universe was dark in a way that nothing in our modern experience can approximate, and it was quiet. There were no stars to produce stellar winds, no galaxies to generate magnetic fields and radio waves, no black holes to consume matter and emit radiation. The only sound, if we can stretch the metaphor, was the slow gravitational whispering of matter pulling on matter. Dark matter was doing most of the heavy lifting. Ordinary matter was following along, falling into the gravitational wells that dark matter had carved out of the cosmic fabric. During the Dark Ages, the temperature of the universe continued to drop as the expansion stretched the remaining photons to longer and longer wavelengths. By the time the Dark Ages ended, the temperature of the cosmic microwave background had fallen to roughly 60 Kelvin, about minus 213 degrees Celsius. The gas itself was even colder in most places because it had decoupled from the radiation and was cooling on its own as it expanded. In the densest regions where gas was accumulating under the influence of gravity, the temperature was beginning to rise as the gas was compressed. These dense warming regions were the cradles where the first stars would soon ignite. Gravity is patient. It does not rush. It works on timescales that make human lifetimes look like the blink of a firefly. But it is also relentless. Wherever the gas was slightly denser than average gravity pulled more gas toward it. And wherever more gas accumulated, the gravitational pull grew stronger, attracting even more gas from the surrounding space. Over millions of years, these subtle density differences grew into larger and larger concentrations of gas. Dark matter played a crucial role in this process. Dark matter is a form of matter that does not interact with light. It does not emit, absorb, or reflect photons, but it does exert gravitational force, and there is roughly 5 times more dark matter in the universe than ordinary matter. The dark matter clumped together first, forming vast invisible scaffolding, and ordinary matter followed, falling into the gravitational wells that dark matter had created. Eventually, some of these gas clouds became dense enough and hot enough for nuclear fusion to begin. Hydrogen atoms were squeezed together so tightly that they fused into helium, releasing enormous amounts of energy in the process. The first stars ignited, and when they did, they ended the Dark Ages with a burst of ultraviolet light that began to transform the universe around them. These first stars were unlike anything that exists today. They were massive. Some estimates suggest the earliest stars could have been 100 to 1,000 times more massive than our Sun. They were incredibly hot, burning through their hydrogen fuel at a ferocious rate. And they were short-lived. A star with 100 times the mass of the Sun does not burn for billions of years like our Sun will. It exhausts its fuel in just a few million years and then collapses in a catastrophic explosion called a supernova. The reason these first stars were so large has to do with the composition of the gas from which they formed. Modern stars form from gas that contains heavy elements and dust particles. These impurities help the gas cool efficiently, allowing it to fragment into smaller clumps that produce stars of modest mass like our Sun. But the first generation of stars had no heavy elements to work with. The gas was pure hydrogen and helium, which cools much less efficiently. Without efficient cooling, the gas clouds could not fragment into small pieces. Instead, they collapsed as massive single units, producing stars that were monsters by any modern standard. These giant first-generation stars, known as population 3 stars, would have been extraordinarily luminous. A star with 300 times the mass of the Sun would shine millions of times brighter than the Sun, producing intense ultraviolet radiation that would ionize the gas around it for enormous distances. These were the lighthouses that ended the cosmic dark ages. Their brilliance cut through the neutral hydrogen fog and began the process of clearing the universe that would eventually allow light to travel freely across cosmic distances. The supernovae that ended the lives of these massive first stars were among the most energetic events in the history of the universe. They scattered the heavy elements that the star had forged in its core elements like carbon, oxygen, nitrogen, and iron into the surrounding space. These elements would eventually become the building blocks of planets, oceans, and living things. Every atom of carbon in your body was forged in the core of a star that died before our Sun was born. The light from these first stars did something else that was critically important. The ultraviolet radiation pouring out of them began to strip the electrons off the neutral hydrogen atoms that filled the surrounding space. This process is called reionization, and it transformed the universe from a cold, neutral fog into the hot, ionized state that it remains in today. Reionization did not happen all at once. It started in small bubbles around the first stars and galaxy clusters, and then these bubbles grew and merged until eventually the entire universe was reionized. This process took hundreds of millions of years, and it is one of the key events that the James Webb Space Telescope was designed to study. The standard model of cosmic evolution that scientists developed over the past several decades tells a specific story about what happened next. After the first stars formed, they began to cluster together under the influence of gravity. Small groups of stars merged into larger groups. Those larger groups merged into even larger ones. Over billions of years, this process of hierarchical merging built the galaxies we see today. Small galaxies collided and combined to form medium galaxies. Medium galaxies collided to form large ones. The Milky Way itself is the product of dozens or perhaps hundreds of smaller galaxies that merged together over billions of years of cosmic history. This model is elegant. It is mathematically consistent. It agrees with most of the observations we have made of the nearby universe, and it makes a very specific prediction about the early universe. In the first few 100 million years after the Big Bang, galaxies should be small, faint and primitive. They should contain relatively few stars. They should be irregular in shape, because they have not yet had time to settle into the beautiful spiral and elliptical forms that characterize mature galaxies. The idea that you could find a galaxy as massive and as structured as the Milky Way existing just 500 million years after the Big Bang is, according to this model, essentially impossible. There simply has not been enough time for the merging process to produce something that large. This is why the James Webb Space Telescope was built. Not to confirm what we already knew, but to look further back in time than any telescope before it, and test whether our models of cosmic evolution actually match reality. And the answer, based on the first 2 years of observations, is deeply unsettling. They do not match. Something happened in the early universe that our models did not predict and cannot easily explain. The universe grew up faster than anyone thought possible. The James Webb Space Telescope is the most powerful space observatory ever constructed. It is the product of over 25 years of development, the combined effort of NASA, the European Space Agency, and the Canadian Space Agency, and a total investment of roughly $10 billion. The telescope launched on December 25, 2021, aboard an Ariane 5 rocket from the European spaceport in Kourou, French Guiana. It then traveled to a point in space called the Second Lagrange Point, or L2, located roughly 1.5 million kilometers from Earth on the side opposite the Sun. At this location, the gravitational forces of the Earth and Sun combine to create a stable point where the telescope can orbit while keeping its sensitive instruments permanently shielded from the heat and light of the Sun. The design of the telescope is extraordinary. Its primary mirror is 6.5 meters across, made up of 18 hexagonal segments of gold-coated beryllium that unfold after launch like the petals of a flower. This mirror is roughly 2.7 times larger in diameter than the Hubble Space Telescope's mirror, which gives it roughly 6 times more light-collecting area. But the true advantage of James Webb is not just its size, it is its wavelength. While Hubble primarily observes invisible and ultraviolet light, James Webb is designed to observe in the infrared, and this is critically important for studying the early universe. Light from the most distant objects in the universe has been traveling for billions of years. During that time, the expansion of the universe has been stretching the wavelength of that light. A photon that was emitted as visible light by a star in the early universe has been stretched during its journey until it arrives at our telescopes as infrared light. The more distant the object, the more the light has been stretched, and the further into the infrared it has been shifted. This stretching of light is called redshift, and it is one of the most important tools in observational cosmology. You can think of redshift like this. Imagine drawing a wave on a rubber band and then stretching the rubber band. As the band stretches, the peaks of the wave move further apart. The wavelength gets longer. Light works the same way. As the universe expands, the wavelength of light traveling through it gets stretched. Blue light becomes red light. Red light becomes infrared light. And the light from the very first galaxies has been stretched so far that it is now deep in the infrared invisible to telescopes like Hubble that primarily see visible light. This is why James Webb was needed. To see the first galaxies, we needed a telescope that could see infrared light with extraordinary sensitivity. And that is exactly what James Webb delivers. Its infrared instruments are so sensitive that they can detect the faint glow of a galaxy that has been stretched and dimmed by 13 billion years of cosmic expansion. It can see things that are literally too far away and too old for any other telescope to observe. When James Webb began its science operations in mid-2022, one of its first major observing programs was a deep survey of a small patch of sky, using its near-infrared camera an instrument designed to capture images in the near-infrared portion of the spectrum. These surveys had names like CEERS, which stands for the Cosmic Evolution Early Release Science Survey, and GLASS, the Grism Lens Amplified Survey from space. The goal of these surveys was simple in concept, but staggering in ambition. Point the most powerful telescope ever built at a seemingly empty patch of sky and see what is there. Look as deep into the universe as possible. Find the most distant, most ancient objects that exist, and compare what you find to what our models predict should be there. The results came back within months, and they were not what anyone expected. The astronomers analyzing the CEERS survey data found galaxies at redshifts of 10, 11, 12, and possibly even higher. To put those numbers in context, a redshift of 10 means the light from that galaxy was emitted when the universe was only about 480 million years old. A redshift of 12 means the light was emitted when the universe was roughly 350 million years old. These are staggering numbers. The universe is 13.8 billion years old. Finding a galaxy at redshift 12 means you are looking at something that existed when the universe was roughly 2.5% of its current age. It is like finding a fully developed oak tree in a forest that was planted last Tuesday. But the distance alone was not the shocking part. Astronomers had expected to find some galaxies at these extreme redshifts. The models predicted that the first galaxies should be forming around this time. What the models did not predict was the size and maturity of what they found. These were not the small, faint, irregular protogalaxies that the hierarchical merging model had led everyone to expect. Some of them were massive, shockingly massive. Some appeared to contain tens of billions of stars. A few candidates seemed to have stellar masses, rivaling that of the present-day Milky Way, which contains roughly 200 to 400 billion stars and has had 13 billion years to grow to that size. The data was clear. The models were not. The first reaction within the scientific community was cautious skepticism. Extraordinary claims require extraordinary evidence, and the claim that massive galaxies existed just a few 100 million years after the Big Bang is about as extraordinary as it gets. The initial estimates of stellar mass in these early galaxies were based on photometric observations, which means they were derived from the brightness and color of the galaxies as captured by the telescope's cameras. These estimates involve assumptions about the types of stars present, the amount of dust, and the history of star formation in the galaxy. If any of those assumptions were wrong, the mass estimates could be significantly off. And indeed, some of the initial candidates did turn out to be less extreme than first reported. When follow-up spectroscopic observations were performed, which provide much more precise measurements of distance and composition, a few of the galaxies were found to be at lower redshifts than originally estimated. They were still distant and still impressive, but they were not quite the universe breakers they had initially appeared to be. However, and this is the critical point, not all of them went away. After the initial round of corrections and confirmations, a significant number of these surprisingly massive early galaxies remained. The spectroscopic data confirmed their extreme distances. The mass estimates, while refined downward in some cases, still indicated galaxies that were far too massive and far too mature for their age, according to standard models. The universe breaker problem did not disappear with better data. It shrank somewhat, but it persisted. And for many cosmologists, that persistence is the most troubling part. One of the most studied examples is a galaxy designated Maisie's Galaxy, named after the daughter of the astronomer who first identified it in the CEERS data. Maisie's Galaxy was confirmed through spectroscopy to exist at a redshift of approximately 11.4. meaning its light was emitted when the universe was only about 390 million years old. While Maisie's galaxy turned out to be somewhat less massive than initial photometric estimates suggested, it is still a remarkably complex object for its age. It shows evidence of active star formation and a chemical composition that indicates multiple generations of stars had already lived and died within it by the time we are seeing it. Multiple generations of stars in less than 400 million years. That is an extraordinary pace of stellar evolution. Another striking case involves a group of galaxies detected at redshifts around 10 in the GLASS survey. These galaxies appear to be surprisingly bright, and some show spectral features indicating the presence of elements heavier than hydrogen and helium. These heavier elements can only be produced inside stars, which means that by the time we are observing these galaxies, stars had already formed, evolved, exploded as supernovae, and enriched the surrounding gas with their processed material. And then new stars had formed from that enriched gas. This entire cycle of stellar birth, death, and rebirth had to happen within the first 500 million years of cosmic history. That is much faster than standard models had predicted. But perhaps the most unsettling discoveries involve galaxies that are not just massive, but also structurally mature. Some of the galaxies detected by James Webb at high redshifts show evidence of organized structures, disc-like shapes, spiral arms, central bulges. These are features associated with galaxies that have had billions of years to settle into gravitational equilibrium. Finding them in galaxies that are only a few 100 million years old is like finding a city with skyscrapers, highways, and subway systems on a continent that was only discovered a week ago. The infrastructure should not be there yet. The time to build it should not have been available. So what is going on? How can these galaxies exist? There are several possible explanations, and each one, if true, would have profound implications for our understanding of the cosmos. The first, and perhaps most conservative explanation, is that our models of star formation in the early universe are simply wrong. Not fundamentally wrong. Not throw out the textbooks wrong, but wrong in the specific details of how efficiently gas was converted into stars in the first few 100 million years. The standard models assume that star formation in the early universe proceeded at roughly the same efficiency as we observe in nearby galaxies today. But what if the conditions in the early universe allowed for much more efficient star formation? What if the pristine hydrogen gas that filled the early cosmos could collapse into stars more quickly and more completely than the metal-enriched, dust-filled gas in modern galaxies? There are reasons to think this might be the case. The first generation of stars formed from gas that contain no heavy elements and no dust. Dust plays an important role in modern star formation because it helps gas clouds cool and fragment into smaller clumps. Without dust, the cooling process works differently, and some theoretical models suggest it could actually lead to the formation of more massive stars and more concentrated bursts of star formation. If the first episodes of star formation were more intense and more efficient than we assumed, then galaxies could build up stellar mass much faster than our models predicted, without needing to change anything fundamental about the Big Bang or the nature of dark matter. This explanation is appealing because it preserves the basic framework of cosmology while adjusting a specific parameter. But it has limits. Even with maximally efficient star formation, there is still a ceiling on how much stellar mass can accumulate in a few 100 million years. The gas has to collapse, the stars have to form, and the process takes time, no matter how efficient it is. Some of the most massive galaxy candidates detected by James Webb push against this ceiling uncomfortably hard. They require star formation efficiencies that approach 100%, meaning nearly all available gas would need to be converted into stars with almost no waste. In the local universe, typical star formation efficiencies are more like 10 to 30%. A jump to near 100% efficiency would itself require an explanation. The second explanation goes deeper and challenges something more fundamental. What if the problem is not with our models of star formation, but with our models of dark matter? In the standard model of cosmology, dark matter is cold. This does not mean its temperature is low in the everyday sense. It means that dark matter particles move slowly relative to the speed of light. Cold, dark matter clumps effectively under gravity, forming dense halos that serve as the gravitational scaffolding for galaxy formation. The cold dark matter model has been extraordinarily successful at explaining the large-scale structure of the universe, the distribution of galaxy clusters, the pattern of the cosmic microwave background, and many other observations. But the cold dark matter model also makes specific predictions about the early universe. It predicts that dark matter halos in the first few 100 million years should be relatively small. Large halos should take time to build up through merging, just like the galaxies themselves. If the galaxies detected by James Webb are truly as massive as they appear, then the dark matter halos hosting them must also be very large. And producing very large dark matter halos that early in cosmic history is difficult within the standard cold dark matter framework. Some theorists have suggested that dark matter might have properties that allow it to clump more effectively in the early universe than the standard cold dark matter model predicts. One possibility is that dark matter particles interact with each other through forces beyond gravity, forces that could enhance the rate of halo formation under certain conditions. Another possibility is that dark matter particles have a small but non-zero self-interaction that allows them to exchange energy and momentum in ways that affect how halos form and evolve. These ideas fall under the broad category of alternative dark matter models, and while they are speculative, they are being taken increasingly seriously in light of the James Webb observations. The self-interacting dark matter hypothesis is particularly interesting because it could solve multiple problems simultaneously. In addition to potentially explaining the early galaxy anomalies, self-interacting dark matter could also address long-standing discrepancies between the predictions of cold dark matter models and observations of small-scale structure in the nearby universe. For example, cold dark matter simulations predict that galaxies should have dense central cusps of dark matter, but observations of many galaxies show flatter, less concentrated central profiles. Self-interactions between dark matter particles could transfer energy from the dense center to the outskirts of the halo, smoothing out the cusp and producing profiles that better match observations. If the same modification that solves the small-scale structure problems also helps explain the early galaxy observations, it would be a compelling indication that we need to revise our understanding of dark matter. Another alternative that has gained attention involves warm dark matter. Unlike cold dark matter, which moves slowly and clumps effectively on all scales, warm dark matter particles move faster, and their thermal motion prevents them from clumping on the smallest scales. This suppresses the formation of small dark matter halos while leaving large halos relatively unaffected. At first glance, this seems like it would make the early galaxy problem worse, not better, because it would reduce the number of small building blocks available for hierarchical merging. But some theorists have pointed out that warm dark matter could actually help if the suppression of small halos is accompanied by an enhancement in the rate of star formation within the halos that do form. With fewer but larger halos forming earlier, and with more gas concentrated in each one, the conditions for rapid galaxy growth might actually be more favorable than in the standard cold, dark matter scenario. Testing these alternative dark matter models requires a combination of observations from multiple sources. James Webb provides data on the abundance and properties of early galaxies. Gravitational lensing observations constrain the distribution of dark matter on various scales. The cosmic microwave background provides information about the total amount of dark matter and its statistical properties, and laboratory experiments like those being conducted at the Large Hadron Collider and in underground detectors are searching for direct evidence of dark matter particles and their interactions. No single observation can definitively distinguish between different dark matter models. But the combination of all these data sets, each probing different aspects of dark matter behavior, will gradually narrow the range of possibilities and point toward the correct description. There is also a more radical possibility. What if dark matter is not a single type of particle, but a family of particles with different properties? What if some fraction of dark matter is cold and behaves exactly as the standard model predicts, while another fraction has different properties that allow it to influence galaxy formation in ways we have not yet accounted for? This kind of mixed dark matter scenario could potentially explain why the standard model works well for most observations, while failing to predict the extreme early galaxies detected by James Webb. But wait. The galaxy mass problem is not the only anomaly that James Webb has uncovered in the early universe. There is another puzzle that is arguably even more perplexing, and it involves not galaxies, but the supermassive black holes sitting at their centers. Every large galaxy in the present-day universe appears to harbor a supermassive black hole at its center. The Milky Way has one called Sagittarius A that has a mass roughly 4 million times that of the Sun. Some galaxies have central black holes that are billions of times more massive than the Sun. These objects are mind-boggling in their scale. A black hole with a mass of 1 billion solar masses has an event horizon, the boundary beyond which nothing can escape, that is larger than the entire orbit of Neptune around the Sun. The standard model for how these supermassive black holes form is a scaled-up version of how ordinary black holes form. When a very massive star runs out of fuel and collapses, the core can be compressed into a black hole with a mass of perhaps 10 to 100 times that of the Sun. This stellar mass black hole then grows by consuming gas dust and other matter from its surroundings. Over time, it merges with other black holes. Gas spirals inward, forming a superheated accretion disk that gradually feeds the black hole. Through this slow process of accretion and merging, the black hole grows from stellar mass to supermassive over billions of years. But there is a speed limit on this growth. A black hole cannot consume matter at an unlimited rate. As gas falls toward the black hole, it heats up to extraordinary temperatures and begins to radiate intensely. This radiation exerts an outward pressure on the infalling gas, pushing it away from the black hole and limiting the rate at which new material can be added. This maximum accretion rate is called the Eddington limit, and it sets a theoretical ceiling on how fast a black hole can grow. Given the Eddington limit starting from a stellar mass black hole of, say, 100 solar masses and growing at the maximum possible rate, it takes roughly 1 billion years to build a supermassive black hole of 1 billion solar masses. This timeline fits comfortably within the age of the universe for black holes that we observe in galaxies at moderate distances. But James Webb has found supermassive black holes at distances that correspond to the first billion years of cosmic history. And some of these black holes appear to already have masses of hundreds of millions or even billions of solar masses. They are too big for their age, just like the galaxies that host them. One of the most remarkable examples was discovered by a team using James Webb to study a galaxy called GNZ11, one of the most distant galaxies known. Spectroscopic observations revealed that GNZ11 harbors an actively feeding supermassive black hole at its center. The galaxy existed when the universe was only about 430 million years old. The estimated mass of the black hole is roughly 1.6 million solar masses. While that is modest compared to the monsters found in nearby galaxies, it is still far more massive than what standard accretion models predict should be possible in less than 500 million years of cosmic history. Even more striking, other surveys have uncovered candidates for even more massive black holes at comparable or greater distances. A galaxy identified in the SEER survey appears to host a black hole with a mass potentially exceeding 10 million solar masses at a redshift of around 8.7, corresponding to roughly 600 million years after the Big Bang. If confirmed, building a black hole that massive in that shorter time would require either sustained accretion at or above the Eddington limit for nearly the entire history of the universe up to that point, or it would require starting from a much more massive seed than a typical stellar mass black hole. This seed mass problem is one of the hottest topics in theoretical astrophysics right now. If supermassive black holes cannot grow fast enough from stellar mass seeds to match what James Webb is observing, then the seeds themselves must have been larger. But how do you make a large seed black hole? Several ideas have been proposed, and each one opens new questions. One possibility is called direct collapse. In certain conditions in the early universe, a massive cloud of pristine hydrogen gas could collapse directly into a black hole without first forming a star. If the gas cloud is large enough, and if it collapses rapidly enough, it could produce a black hole with a mass of 1,000 to 100,000 solar masses in a single event. This is called a direct collapse black hole, and it would provide a much more massive starting point for subsequent growth through accretion. The physics behind direct collapse is fascinating. Normally, when a gas cloud collapses under gravity, it heats up. And as it heats up, it begins to radiate energy, which allows it to cool and continue collapsing. This cooling process is what leads to the fragmentation of the cloud into smaller pieces that eventually become individual stars. But under very specific conditions, the cooling process can be suppressed. If the gas cloud is bathed in a strong field of ultraviolet radiation from nearby stars or galaxies, the ultraviolet photons can destroy the molecular hydrogen that would otherwise serve as the primary coolant. Without this coolant, the gas cannot fragment. It continues to collapse as a single massive unit, growing hotter and denser until it becomes so compact that it collapses directly into a black hole. The mass of the resulting black hole depends on the mass of the original gas cloud and the efficiency of the collapse. Theoretical calculations suggest that direct collapse could produce black holes with masses of tens of thousands to hundreds of thousands of solar masses. These are far more massive than any stellar mass black hole, and they would provide a much more comfortable starting point for growing into the supermassive black holes that James Webb is detecting at high redshifts. The problem is that direct collapse requires very specific conditions. The gas cloud must be free of heavy elements and dust, which would cause it to cool and fragment into smaller clumps before it can collapse into a single massive object. It also requires a strong background of ultraviolet radiation to suppress the formation of molecular hydrogen, which is one of the primary cooling agents in pristine gas. Finding environments in the early universe where all these conditions are met simultaneously is theoretically possible, but it may not be common enough to explain all the supermassive black holes that James Webb is discovering. There is also the question of observational signatures. A direct collapse event would produce a distinctive electromagnetic signal as the infalling gas heats up to enormous temperatures before crossing the event horizon. Future telescopes might be able to detect these signals if they know what to look for. Several theoretical groups are currently calculating the expected signatures of direct collapse events at different redshifts, creating templates that observers can use to search the James Webb data for evidence of this process in action. Another possibility is that the first generation of stars was even more massive than we currently believe. If some of the first stars had masses of several thousand solar masses, which is speculative but not impossible. Given the unique conditions of the early universe, then the black holes they left behind when they died could have been massive enough to serve as seeds for rapid subsequent growth. These hypothetical supermassive first-generation stars are sometimes called quasi-stars, and they represent an extreme end of the theoretical spectrum for early stellar evolution. Third possibility involves the merging of smaller black holes in dense stellar environments. If the first star clusters were extremely dense, then black holes within those clusters could have merged repeatedly through gravitational interactions, building up mass much faster than accretion alone would allow. Each merger event would produce a larger black hole that would then be better able to attract and consume surrounding gas, accelerating its growth even further. This runaway merging scenario is mathematically plausible, but it requires initial conditions that are not well constrained by current observations. The black hole mass problem is intimately connected to the galaxy mass problem, because supermassive black holes and their host galaxies appear to grow together. In the nearby universe, there is a tight relationship between the mass of a galaxy's central black hole and the mass of the galaxy's central bulge of stars. This relationship suggests that the growth of the black hole and the growth of the galaxy are not independent processes. They are linked possibly through feedback mechanisms, where the energy output of the accreting black hole regulates the rate of star formation in the surrounding galaxy. If this relationship between black hole mass and galaxy mass holds in the early universe as well as it does in the nearby universe, then the discovery of massive black holes at high redshifts implies the existence of massive galaxies at high redshifts and vice versa. The two problems reinforce each other. Every massive early black hole that James Webb discovers adds weight to the evidence that galaxies grew faster than expected. And every massive early galaxy adds weight to the evidence that black holes grew faster than expected. The anomalies are not independent. They are two faces of the same deep puzzle, and the puzzle extends further still. Because the galaxies and black holes are not the only things that are too big too early. The large-scale structure of the universe itself may be showing signs of premature maturity. In the standard model of cosmology, the universe develops structure gradually. First, small dark matter halos form. Then these halos merge into larger ones. Galaxies form within these halos. Galaxy groups and clusters form as halos continue to merge, and eventually the vast cosmic web of filaments and voids that characterizes the large-scale structure of the universe takes shape over billions of years. This process is driven by gravity, and it follows a specific timeline. Large structures should not be present in the very early universe because there has not been enough time for gravity to assemble them. But some observations from James Webb and other telescopes suggest that the early universe may have had more large-scale structure than expected. Surveys have found groupings of galaxies at high redshifts, that appear to be more clustered than the standard model predicts. Some of these groupings might be the precursors of the massive galaxy clusters we see in the nearby universe. If they are genuinely more abundant or more massive than predicted, it would suggest that the process of structure formation started earlier or proceeded faster than our models account for. One particularly intriguing observation involves a candidate protocluster detected at a redshift of approximately 7.9, corresponding to about 650 million years after the Big Bang. This structure appears to contain multiple bright galaxies concentrated in a relatively small volume of space. If confirmed as a genuine gravitationally bound structure, it would be one of the earliest known examples of galaxies beginning to cluster together. And the concentration of mass in such a small volume at such an early time is difficult to reconcile with the standard timeline of structure formation. These observations of premature large-scale structure add another dimension to the puzzle. It is not just individual galaxies and individual black holes that are too big too early. It may be the entire pattern of structure in the universe that developed faster than we thought. The universe did not just grow up fast in isolated pockets. It may have grown up fast everywhere. So where does this leave us? We have galaxies that are too massive, black holes that are too big, and possibly large-scale structures that are too developed, all of them existing at a time in cosmic history when, according to our best models, they should not yet be possible. Something is either wrong with the observations or something is wrong with the models. And as the observations continue to be confirmed and refined, the weight of evidence is increasingly pointing toward the models. To understand what might need to change, we should look more carefully at the foundation of our current cosmological framework. The standard model of cosmology is built on a set of assumptions and measurements that have been refined over the past century. At its core is the lambda cold dark matter model, often abbreviated as lambda CDM. Lambda represents dark energy, the mysterious force that is driving the accelerating expansion of the universe. CDM stands for cold dark matter, the invisible matter that provides the gravitational scaffolding for structure formation. Lambda CDM has been spectacularly successful. It correctly predicts the pattern of temperature fluctuations in the cosmic microwave background. It explains the observed distribution of galaxies on the larger scales. It accounts for the abundances of light elements like hydrogen, helium, and lithium that were produced in the first few minutes after the Big Bang. And it provides a framework for understanding how the universe has expanded and evolved over the past 13.8 billion years. For these reasons, lambda CDM has been the dominant model in cosmology for over 2 decades, and it has been supported by an impressive body of observational evidence. But lambda CDM is not a complete theory. It describes what the universe does, but it does not fully explain why. We do not know what dark energy is. We do not know what dark matter is made of. We do not understand why the cosmological constant has the value it has, and we cannot explain certain anomalies in the data that have been accumulating for years before James Webb was even launched. The most famous of these pre-existing anomalies is the Hubble tension. The Hubble constant is a number that describes the rate at which the universe is expanding. It tells us how fast distant galaxies are moving away from us as a function of their distance. If you know the Hubble constant, you can calculate the age of the universe, the distance to remote objects, and the overall geometry of spacetime. It is one of the most important numbers in all of cosmology. The problem is that 2 different methods of measuring the Hubble constant give 2 different answers. The first method uses observations of the cosmic microwave background to infer the expansion rate of the early universe and then extrapolates that rate forward to the present day. This method, based on data from the Planck satellite, gives a Hubble constant of approximately 67.4 kilometers per second per megaparsec. A megaparsec is a unit of distance used in cosmology equal to roughly 3.26 million light-years. So a Hubble constant of 67.4 means that for every megaparsec of distance, galaxies are receding from us at 67.4 kilometers per second. A galaxy that is 100 megaparsecs away is receding at 6740 kilometers per second. A galaxy that is 1000 megaparsecs away is receding at 16,400 kilometers per second. The second method uses observations of nearby objects, specifically a class of exploding stars called type Ia supernovae and a type of pulsating star called Cepheid variables, to directly measure the expansion rate of the nearby universe. Type Ia supernovae are particularly useful because they all explode with approximately the same intrinsic brightness, making them cosmic standard candles. By comparing the intrinsic brightness of a type Ia supernova to its observed brightness, astronomers can calculate its distance. And by measuring its redshift, they can determine how fast it is receding. Combining distance and recession speed gives the Hubble constant. Cepheid variables serve as a stepping stone in this measurement. These are stars that pulsate in brightness with a period that is directly related to their intrinsic luminosity. By measuring the period of a Cepheid variable, astronomers can determine its true brightness and therefore its distance. Cepheids are used to calibrate the distances to nearby galaxies that also contain type Ia supernovae, creating a chain of distance measurements called the cosmic distance ladder that extends from the nearby universe to cosmological distances. This second method, led by a team using the Hubble Space Telescope and more recently calibrated using James Webb observations of Cepheids, gives a value of approximately 73.0 kilometers per second per megaparsec. The difference between these two numbers might seem small, but it is statistically significant. The measurements are precise enough that the probability of the discrepancy being due to random error is extremely low. Something real is causing the disagreement. Either one or both of the measurement methods has a systematic error that we have not identified, or there is something about the physics of the universe that our models do not capture. The Hubble tension has been one of the biggest unresolved problems in cosmology for years, and James Webb has added fuel to the debate. Early observations from James Webb have been used to recalibrate the cosmic distance ladder, the chain of measurements that links nearby distance indicators to more distant ones. Some of these recalibrations have supported the higher value of the Hubble constant derived from nearby observations. If the higher value is correct, it would mean the universe is expanding faster than lambda CDM predicts, which in turn would affect our calculations of cosmic age and the timeline of structure formation. Here is why this matters for the early galaxy problem. The age of the universe is directly related to the expansion rate. If the universe is expanding faster than we thought, then it might also be slightly younger than we thought. And if the universe is younger, then the problem of finding massive galaxies at high redshifts becomes even worse, because there is even less time available for them to have formed. Alternatively, if there is some unknown physics that causes the expansion rate to vary over time in ways that lambda CDM does not account for, then the relationship between redshift and cosmic age might be different from what we currently calculate. Galaxies at redshift 10 might not correspond to 480 million years after the Big Bang. They might correspond to a different age entirely depending on the details of the expansion history. This is one of the most subtle and potentially profound implications of the James Webb discoveries. The telescope is not just finding objects that are too big for their age. It is raising questions about whether we are correctly measuring that age in the first place. The rulers we use to measure cosmic time and distance are calibrated using assumptions that may need to be revised. And if those assumptions change, then our entire map of the universe changes with them. Some physicists have gone further and proposed that the James Webb observations might be hints of entirely new physics. One speculative idea is that the gravitational constant, the fundamental number that determines the strength of gravity, might not be truly constant. If gravity was slightly stronger in the early universe, then matter would have clumped together faster and structure would have formed more quickly. This would help explain the early galaxies and the early black holes without needing to change anything about dark matter or star formation efficiency. But varying constants are extremely difficult to reconcile with other observations, and most physicists regard this idea as a last resort. Another speculative idea involves modifications to the theory of inflation. Inflation is the period of extremely rapid expansion that occurred in the first fraction of a second after the Big Bang. The details of inflation determine the statistical properties of the density fluctuations that seeded all subsequent structure formation. If inflation produced slightly different fluctuations than we currently believe, specifically if it produced more pronounced density peaks on certain scales, then the early universe might have had a head start on structure formation. Some theorists have explored models of inflation that could produce this kind of enhanced structure without violating other observational constraints. These models are mathematically complex and are still being evaluated against the growing body of James Webb data. There is also the possibility that the early universe contained a significant population of objects that we have not yet identified. For example, some models predict the existence of primordial black holes that formed not from the collapse of stars, but from the direct collapse of extremely dense regions in the very early universe, possibly during or immediately after inflation. If primordial black holes existed in sufficient numbers, they could have served as seeds for rapid galaxy and black hole growth, providing a head start that would help explain the James Webb observations. The idea of primordial black holes has been around for decades, but it has gained renewed interest in light of the early galaxy discoveries. Each of these explanations addresses a piece of the puzzle, but none of them solves the entire thing. The reality is that we are probably dealing with a combination of factors. Star formation in the early universe was likely more efficient than we assumed. Dark matter may have properties that allowed slightly faster structure formation. The relationship between redshift and cosmic age may need refinement, and there may be populations of objects like primordial black holes or direct collapse black holes that we have not yet fully accounted for. The complete picture will likely involve revisions to multiple aspects of our cosmological models rather than a single dramatic breakthrough. And this is exactly what makes the James Webb era so exciting for science. We are not just learning new facts about distant objects. We are testing the foundations of our understanding of the universe. Every observation that disagrees with our models is not a failure. It is an invitation. An invitation to dig deeper, think harder, and build a more complete picture of how the cosmos works. Let us now look at some of the specific techniques and observations that have been most important in characterizing the early galaxies discovered by James Webb. One of the most powerful tools in the astronomer's arsenal is spectroscopy. While an image tells you what an object looks like and how bright it is, a spectrum tells you what it is made of, how fast it is moving, and how far away it is. Spectroscopy works by spreading the light from an object into its component wavelengths, like a prism splitting white light into a rainbow. different elements and molecules absorb and emit light at specific wavelengths, creating a pattern of bright and dark lines in the spectrum that acts as a chemical fingerprint. For distant galaxies, spectroscopy is essential for confirming redshifts. A photometric redshift estimated from the overall color of a galaxy can be useful as a first approximation, but it is subject to significant uncertainties. A spectroscopic redshift measured from the precise positions of emission or absorption lines in the galaxy spectrum is much more reliable. Many of the initial claims about extremely high redshift galaxies from the early James Webb data were based on photometric estimates. As spectroscopic follow-up observations have been conducted, some of these estimates have been confirmed, while others have been revised. The process of confirming a high redshift galaxy spectroscopically is painstaking. The galaxy is typically very faint, and its light has been stretched deep into the infrared. The spectrograph must collect light for many hours to accumulate enough signal to identify spectral features, and the features themselves may be subtle, especially in the spectra of the youngest galaxies, which have had less time to accumulate the heavy elements that produce strong emission lines. Despite these challenges, the spectroscopic confirmation of high redshift galaxies has proceeded steadily. By the end of 2024, dozens of galaxies at redshifts above 10 had been spectroscopically confirmed. Several had been confirmed at redshifts above 12, and at least one candidate, a galaxy identified in the JD survey, had been detected at a redshift of approximately 14, corresponding to roughly 290 million years after the Big Bang. If this redshift is accurate, it would place this galaxy among the very first large structures to have formed in the universe. The spectra of these early galaxies reveal other important information beyond their distances. They show the chemical composition of the gas in and around the galaxies, and what they show is surprising. Many of the earliest galaxies contain detectable amounts of elements heavier than hydrogen and helium elements that can only be produced inside stars. The presence of these elements at such early times confirms that star formation was already well underway, and that at least one full generation of stars had already lived and died by the time we are observing these galaxies. In some cases, the abundances of heavy elements suggest that multiple generations of stellar evolution had occurred, which further compresses the timeline and deepens the puzzle of how so much happened so quickly. The spectra also reveals something about the nature of the light sources within these early galaxies. In some cases, the spectral signatures indicate the presence of very hot massive stars, the kind of luminous blue giants that burn through their fuel quickly and die young. This is consistent with what we would expect in young galaxies that are undergoing their first intense episodes of star formation. But in other cases, the spectra show features that are harder to explain. Some galaxies show signs of an active galactic nucleus, meaning that the supermassive black hole at the center is actively consuming matter and producing intense radiation. The coexistence of vigorous star formation and active black hole accretion in the same galaxy at such an early time raises questions about the feedback mechanisms that are supposed to regulate both processes. In nearby galaxies, there is a well-established relationship between black hole activity and star formation. When a black hole is actively accreting, it produces powerful jets of energy and radiation that heat the surrounding gas and can shut down star formation in the host galaxy. This feedback process is one of the reasons why galaxies in the present-day universe do not grow indefinitely. The black hole acts as a thermostat regulating the rate of star formation by heating or expelling the gas that would otherwise collapse into new stars. But in the very early universe, this feedback relationship may not have been established yet. If both the black hole and the galaxy are growing simultaneously at maximum rate, there may be a brief window where the feedback has not yet caught up, where the galaxy is forming stars as fast as the gas can collapse, while the black hole is also growing as fast as it can consume. This would be a period of maximum cosmic productivity, a frenzy of growth that would produce exactly the kind of oversized galaxies and black holes that James Webb is detecting. But it would also be unstable. Eventually, the black hole would grow powerful enough for its feedback to kick in, the star formation would slow, and the galaxy would begin to evolve more slowly. The question is whether this rapid growth phase is consistent with the physics of gas dynamics and gravity as we understand them, or whether it requires conditions that go beyond our current models. Let us pause here and think about what we are really dealing with from a philosophical standpoint. The James Webb Space Telescope is not just showing us distant objects, it is showing us the universe as it was in its infancy. Every image of a galaxy at redshift 10 or 12 is a baby picture of the cosmos. And what those baby pictures are telling us is that the baby was much more developed than we expected. It was walking before we thought it could crawl. It was building structures before we thought it had the materials. It was performing feats of growth that our models said should take billions of years to achieve, but which somehow happened in mere hundreds of millions. This is not the first time that observations of the universe have forced us to rethink our models. Science advances precisely by encountering the unexpected and then revising its understanding to accommodate the new data. The discovery that the universe is expanding, made by Edwin Hubble in 1929, overturned centuries of belief in a static eternal cosmos. The discovery of the cosmic microwave background in 1965 confirmed the Big Bang theory and eliminated the competing steady-state model. The discovery of dark energy in 1998, based on observations of distant supernovae, revealed that the expansion of the universe is accelerating, a finding so unexpected that it earned its discoverers the Nobel Prize. In each of these cases, the initial reaction of the scientific community was skepticism. The observations were checked and rechecked. Alternative explanations were proposed and tested, and eventually, when the evidence became overwhelming, the models were revised. We may be in the early stages of a similar process right now. The James Webb observations are still relatively new. The data is still being analyzed. Some findings may be revised or overturned as better observations become available. But the broad pattern, the existence of surprisingly mature structures in the very early universe, appears to be robust, and the models will need to evolve to accommodate it. One of the most fascinating aspects of this story is the role of dust. Dust is a mundane-sounding word for something that plays an outsized role in the life of galaxies. In astronomy, dust refers to tiny solid particles, typically a few micrometers or smaller in size, made of silicates, carbon compounds, and other materials produced in the atmospheres and explosions of stars. Dust absorbs ultraviolet and visible light from stars and re-emits that energy as infrared radiation. The presence of dust in a galaxy can dramatically affect how we perceive it. James Webb has revealed that some early galaxies contain significant amounts of dust. This was unexpected because dust is produced by stellar processes, and its presence in very young galaxies implies that those processes had already been operating for some time. The dust absorbs the ultraviolet light from young hot stars and re-emits it in the infrared, which is exactly the wavelength range where James Webb excels. This means that James Webb may be particularly sensitive to detecting dusty early galaxies that would have been invisible to previous telescopes. Hubble, which primarily observes ultraviolet and visible light, would miss a dusty galaxy entirely because all of its light would be absorbed by the dust before it could reach the telescope. This raises an interesting possibility. Perhaps the early universe was not as different from our models as it initially appears. Perhaps the early universe did contain the small, faint protogalaxies that our models predict, but it also contained a population of dusty, massive galaxies that were invisible to previous telescopes. James Webb is not revealing a universe that is fundamentally different from what we expected. It is revealing a universe that was always more complex than we could see with the tools we had. This dust selection effect is an important caveat when interpreting the James Webb data. The telescope is not taking a random sample of early galaxies. It is seeing the galaxies that are brightest in the infrared, which are preferentially the most massive and the most dusty. The small, faint protogalaxies that our models predict are still there. They are just harder to detect even for James Webb. The full picture of the early universe will only emerge when we can combine observations of both the bright, massive galaxies and the faint, small ones and determine the relative numbers of each. Measuring these relative numbers is one of the key goals of current and future James Webb observing programs. Astronomers are using deep field surveys to count the number of galaxies at each brightness level and each redshift. These counts are then compared to the predictions of cosmological models. If the counts at the bright end are higher than predicted, it means there are too many massive galaxies. If the counts at the faint end match predictions, it means the standard model is still correct for typical galaxies and only needs adjustment at the extreme end. The results so far suggest that the bright end counts are indeed higher than expected, confirming that the most massive galaxies are overrepresented in the early universe. But the faint end data is still being collected, and the complete picture remains a work in progress. Another important technique being used to study these early galaxies is gravitational lensing. Gravitational lensing occurs when the gravity of a massive object such as a galaxy cluster bends and magnifies the light from more distant objects behind it. This effect, predicted by Einstein's theory of general relativity, turns the massive foreground cluster into a natural telescope that can magnify the images of background galaxies by factors of 1050 or even more. James Webb has taken advantage of gravitational lensing to study some of the faintest and most distant galaxies in the universe. The physics behind gravitational lensing is elegant and simple in concept. Einstein's theory tells us that mass warps the fabric of space-time. When a photon of light passes near a massive object, it follows the curved path dictated by the warped space-time bending toward the mass. If a distant galaxy is located directly behind a massive foreground cluster, the light from the galaxy is bent around the cluster from multiple directions, creating multiple distorted images of the background galaxy. In some cases, the background galaxy is stretched into a long, thin arc that curves around the foreground cluster like a smile. In other cases, multiple separate images of the same galaxy appear at different positions around the cluster. The magnification provided by gravitational lensing is not uniform. It depends on the precise alignment between the observer, the foreground cluster, and the background galaxy. Some regions of the sky behind the cluster are highly magnified with amplification factors of 50 or more. Other regions are only slightly magnified. By mapping the mass distribution of the foreground cluster, astronomers can calculate the magnification at every point in the field and correct the observed brightness of each background galaxy accordingly. This process is complex and subject to uncertainties in the mass model, but it has been refined over decades of practice and is now a mature and powerful technique. One of the most spectacular examples of gravitational lensing in the James Webb data is a galaxy cluster called Hubble 2744, also known as Pandora's cluster. This massive cluster contains so much matter that it dramatically warps the space-time around it, creating multiple magnified images of background galaxies. James Webb observed this cluster in one of its earliest deep field programs, and the resulting images revealed dozens of extremely distant galaxies that would have been undetectable without the lensing magnification. Some of these galaxies are among the most distant objects ever observed, and their properties are being studied in detail to understand the conditions of the early universe. Gravitational lensing is particularly valuable because it allows astronomers to study galaxies that are intrinsically faint galaxies that do not have the extreme stellar masses or the dust content needed to be directly detected by James Webb. These are the normal galaxies of the early universe, the ones that our models predict should be the most common. By studying them through the magnifying glass of gravitational lensing, we can test whether the standard models are correct for typical galaxies, even if they fail for the extreme outliers. The results from lensing studies have added nuance to the picture. While the most massive early galaxies remain problematic for standard models, the population of more typical galaxies detected through lensing appears to be broadly consistent with predictions. This suggests that the problem may not be with the entire framework of galaxy formation, but specifically with the high mass end of the distribution. Something is allowing a small fraction of galaxies to grow to extreme sizes very quickly, while the majority of galaxies evolve at the pace our models expect. Understanding what sets these extreme galaxies apart from their more typical counterparts is one of the central challenges of post-James Webb cosmology. Let us now dive deeper into some of the specific galaxies that have caused the most excitement and controversy since James Webb began operations. Because the story of the early universe is not just told in statistics and models. It is told in individual objects, each one a unique window into conditions that existed billions of years ago. One of the first and most famous discoveries was a galaxy candidate, initially designated as Sears 1749. This object appeared in some of the earliest James Webb deep field data, and its photometric colors suggested an extraordinary redshift possibly as high as 16. If accurate, this would have placed it at a time when the universe was only about 250 million years old. The announcement generated enormous excitement and considerable media attention. Here was a galaxy that appeared to exist at a time so early that our models barely allowed for the existence of individual stars, let alone an entire galaxy. But as with many of the earliest James Webb discoveries, subsequent analysis tempered the initial excitement. Spectroscopic follow-up observations revealed that Sears 1749 was actually at a much lower redshift, around 5. It was still a distant and interesting galaxy, but not the cosmic record breaker it initially appeared to be. The misidentification was caused by the photometric degeneracy problem, a well-known limitation of estimating redshifts from colors alone. Certain combinations of galaxy age, dust content, and star formation history can produce colors that mimic those of a much more distant object. Only spectroscopy can break this degeneracy and distinguish between a heavily reddened nearby galaxy and a genuinely primordial one. This episode illustrates an important point about the process of scientific discovery. The initial flood of data from a revolutionary new telescope inevitably produces some false alarms. Objects that appear extraordinary at first glance sometimes turn out to be more ordinary upon closer inspection. This is not a failure of the science. It is the science working exactly as it should. The photometric discoveries raise the alarm. The spectroscopic follow-up confirms or denies, and the true picture emerges gradually through this iterative process of claim and verification. But the false alarm should not obscure the genuine discoveries, and there have been many. The galaxy GN-Z11, originally detected by Hubble and confirmed by James Webb, remains one of the most important objects in the study of the early universe, at a spectroscopically confirmed redshift of 10.6, corresponding to about 420 million years after the Big Bang. GN-Z11 is one of the most distant galaxies with detailed spectral information available. Its spectrum reveals the presence of nitrogen, carbon, and other elements heavier than hydrogen and helium. The nitrogen abundance in particular is surprisingly high, suggesting that the chemical enrichment of this galaxy proceeded faster than expected. The high nitrogen abundance in GN-Z11 has led to some intriguing hypotheses. One possibility is that the galaxy experienced an extremely intense burst of star formation in its early history, producing a large population of very massive stars that evolved quickly and scattered heavy elements into the surrounding gas. Another possibility is that the unusual chemistry reflects the influence of the central black hole, whose energetic radiation could alter the chemical pathways through which heavy elements are produced in the surrounding gas. A third possibility is that the galaxy has undergone some unusual form of chemical evolution that our models do not currently capture. Another landmark object is JADES GS Z14-0, a galaxy detected in the JADES survey at a spectroscopic redshift of approximately 14.2. This places at roughly 290 million years after the Big Bang, making it one of the most distant spectroscopically confirmed galaxies as of early 2025. What makes this galaxy particularly remarkable is not just its distance but its brightness. It is significantly brighter than what models predict for a galaxy at this redshift, suggesting either an unusually high rate of star formation or contributions from an active galactic nucleus, or both. The spectrum of JADES GS Z14-0 shows strong emission from ionized hydrogen, indicating vigorous ongoing star formation. The galaxy appears to be converting gas into stars at a rate that is many times higher than what is typical for galaxies at this distance in standard cosmological simulations. If confirmed, this rate of star formation in such a young galaxy adds further evidence to the growing case that the early universe was a more productive place than our models anticipated. There are also the so-called little red dots, a class of compact red objects that have been discovered in large numbers by James Webb. These objects are small in angular size, appear red in the infrared, and are found at a wide range of redshifts from roughly 5 to beyond 10. Their nature is still debated. Some appear to be compact galaxies with significant dust reddening. Others show spectral signatures consistent with active galactic nuclei, supermassive black holes, that are actively consuming matter and producing copious amounts of radiation. The little red dots are interesting because they might represent a previously unknown phase of galaxy evolution. They could be galaxies in the process of building their central black holes, or they could be galaxies where the black hole is already present and is being fed by rapid inflows of gas. Their compactness suggests that a lot of mass is concentrated in a very small volume, which is consistent with the intense activity implied by their brightness and spectral features. Understanding the little red dots is one of the most active areas of research in the James Webb community, because they may hold clues to how galaxies and black holes co-evolved in the early universe. Then there is the question of the galaxies that James Webb has not found. In science, the absence of expected observations can be just as informative as the presence of unexpected ones. One of the predictions of the Standard Model is that the very first galaxies should have been essentially metal-free, composed entirely of hydrogen and helium, with no heavy elements. These pristine first-generation galaxies are sometimes called population 3 galaxies, after the hypothetical population 3 stars that should have been the first stars to form. Despite extensive searching, James Webb has not yet conclusively identified a population 3 galaxy. Every galaxy observed so far, even the most distant ones, shows at least some evidence of chemical enrichment, meaning that heavier elements are present. This could mean several things. It could mean that the transition from pristine gas to enriched gas happened very quickly within the first few 100 million years, leaving no observable window of pristine galaxy formation. It could mean that population 3 galaxies are extremely faint and have not yet been detected. Or it could mean that our understanding of the first stars and the chemical enrichment process needs revision. The search for population 3 galaxies continues, and it is one of the most important open questions in the field. Finding such a galaxy would provide direct evidence for the theoretical models of the first stars and would help calibrate our understanding of the chemical evolution of the universe. Not finding one despite extensive searching would itself be an important clue that the early universe evolved differently from what current models predict. The variety of objects and phenomena that James Webb has revealed in the early universe paints a picture of a cosmic dawn that was far more complex and diverse than anyone anticipated. The early universe was not a simple place where a few small protogalaxies slowly grew through merging over billions of years. It was a dynamic, rapidly evolving environment where massive galaxies, supermassive black holes, dusty star-forming systems, compact red objects, and possibly the seeds of giant galaxy clusters all coexisted within the first billion years of cosmic history. The diversity of the early universe is in many ways its most surprising feature. This diversity also has implications for how we think about the evolution of galaxies over cosmic time. The traditional picture of galaxy evolution is a relatively orderly process. Galaxies start small and grow through merging. They evolve from irregular to spiral to elliptical as they age and interact with their neighbors. But the James Webb data suggests that this orderly progression may not capture the full story. Some galaxies appear to have arrived at maturity very quickly, bypassing the expected stages of slow growth. Others appear to be in evolutionary states that do not fit neatly into the traditional classification scheme. The early universe may have been a place where multiple pathways to galaxy formation were operating simultaneously, some slow and some fast, some orderly and some chaotic. Understanding these multiple pathways and determining which ones were most common is one of the great challenges that James Webb has placed before the astronomical community. It will require not just more observations, but also more sophisticated theoretical models that can account for the range of behaviors that the data is revealing. The models of galaxy formation that were developed before James Webb were calibrated primarily against observations of the nearby universe. They may have captured the dominant modes of galaxy evolution in the present-day cosmos. But the early universe, with its different conditions, different chemistry, and different energy budgets, may have operated according to different rules. The challenge now is to figure out what those rules were. Let us now explore the concept of redshift in more detail, because it is absolutely central to everything we have been discussing. Redshift is the key that unlocks the distance and age of the objects James Webb is observing, and understanding it deeply helps us appreciate both the power and the limitations of our measurements. Light travels at a fixed speed, roughly 3,000 kilometers per second. nothing with mass can travel faster. This speed is the same in all directions and for all observers, regardless of their motion. It is one of the most fundamental constants in physics. But while the speed of light is constant, the wavelength of light is not. The wavelength can be stretched or compressed by the motion of the source relative to the observer and by the expansion of the space through which the light is traveling. Imagine you are standing by the side of a road and an ambulance drives past you with its siren blaring. As the ambulance approaches, the sound waves are compressed, making the siren sound higher pitched. As the ambulance moves away, the sound waves are stretched, making the siren sound lower pitched. This is the Doppler effect, and it works for light as well as sound. An object moving towards you emits light that is compressed to shorter, bluer wavelengths. An object moving away from you emits light that is stretched to longer, redder wavelengths. But the redshift we observe in distant galaxies is not caused by the galaxies moving through space away from us. It is caused by the expansion of space itself. The galaxies are not flying apart like shrapnel from an explosion. They are sitting still, more or less, while the space between them is expanding. And as that space expands, it stretches the light traveling through it. Every photon of light emitted by a distant galaxy is stretched during its journey to us. The longer the journey, the more the light is stretched. And the more the light is stretched, the higher the redshift. A redshift of 1 means the wavelength of the light has been doubled. A redshift of 10 means the wavelength has been stretched by a factor of 11. A redshift of 14, the highest confirmed by James Webb so far, means the wavelength has been stretched by a factor of 15. Light that was originally emitted in the ultraviolet has been stretched all the way into the infrared by the time it reaches us. This is why James Webb needs to observe in the infrared. The earliest objects in the universe emitted their light in the ultraviolet and visible range. But by the time that light arrives at our telescopes, it has been stretched so far that it is only visible in the infrared. The relationship between redshift and distance is not straightforward, because the expansion rate of the universe has changed over time. In the early universe, expansion was decelerating as gravity pulled on the matter. Then roughly 5 billion years ago, dark energy began to dominate, and the expansion started accelerating. Because the expansion rate changes over time, converting a redshift to a distance or an age requires a detailed model of how the universe has expanded. This is where the Hubble constant and the other parameters of the lambda CDM model come in. They define the expansion history and allow us to translate redshifts into physical distances and cosmic ages. When we say that a galaxy at redshift 14 existed about 290 million years after the Big Bang, that age is calculated using the best fit lambda CDM model. If the model is revised, if the parameters change, then the ages change too. This is why the Hubble tension and the other challenges to lambda CDM are so important for the early galaxy problem. If our model of the expansion history is even slightly wrong, then all of our age estimates for distant objects are also slightly wrong. And at the extreme redshifts where James Webb is operating, even small changes in the model can translate into significant changes in the inferred age and properties of the observed galaxies. This uncertainty in the expansion history is one of the reasons why astronomers are careful to present their results in terms of redshift rather than age or distance. The redshift is an observed quantity. It is measured directly from the spectrum of the galaxy. The age and distance are derived quantities. They depend on the cosmological model. By presenting results in terms of redshift, astronomers can separate the observations from the model-dependent interpretations and allow the data to be reinterpreted as models evolve. Now, let us consider what the James Webb observations mean for our understanding of the reionization of the universe. As we discussed earlier, reionization is the process by which the neutral hydrogen gas that filled the universe after recombination was stripped of its electrons by ultraviolet radiation from the first stars and galaxies. This transformation from a neutral universe to an ionized one was one of the most important events in cosmic history, and it is intimately connected to the question of when and how the first galaxies formed. The standard model of reionization assumes that the process was driven primarily by the ultraviolet light from early galaxies. As galaxies formed and produced stars, those stars emitted ultraviolet radiation that ionized the surrounding hydrogen gas. The ionized bubbles around individual galaxies grew and eventually merged, completing the reionization of the universe by roughly 500 to 800 million years after the Big Bang. But for this model to work, the early galaxies need to produce enough ultraviolet radiation to ionize all the hydrogen in the universe. And this is where the James Webb observations become important. By counting the number of early galaxies and measuring their ultraviolet luminosities, astronomers can estimate whether the known galaxy population was sufficient to drive reionization, or whether additional sources of ionizing radiation are needed. The initial results from James Webb suggest that the early galaxy population was more numerous and more luminous than previously thought. If this is correct, then the galaxies themselves may have been more than sufficient to drive reionization, without needing to invoke exotic sources like decaying dark matter or primordial black holes. In fact, some analyses suggest that the early galaxies were so numerous that they could have reionized the universe earlier than the standard models predict, consistent with some hints from other observations that reionization may have started earlier than previously believed. This earlier start to reionization would have important consequences. It would mean that the first significant star-forming systems appeared sooner than expected, which connect directly to the mystery of the oversized early galaxies. If galaxies were forming earlier and in greater numbers, then there was more time for the most massive ones to grow, which partially alleviates the age problem. But it also creates new questions. Where did all these early galaxies come from? What triggered such widespread star formation so soon after the Big Bang? And does the early onset of reionization require changes to our models of the dark ages and the formation of the first stars? The interplay between reionization and galaxy formation is one of the most active areas of research in the James Webb era. The telescope is providing data on both sides of the equation, measuring the properties of early galaxies, while simultaneously probing the state of the intergalactic medium through which their light travels. By combining these measurements, astronomers hope to build a self-consistent picture of how the cosmic dawn unfolded from the formation of the first stars through the growth of the first galaxies to the completion of reionization. It is a complex puzzle with many interlocking pieces, and James Webb is providing the observations needed to put those pieces together. But James Webb is not working alone. Several other observatories and experiments are contributing to the study of the early universe in ways that complement the telescope's capabilities. Ground-based telescopes like the Atacama Large Millimeter Array in Chile observe the early universe at sub-millimeter wavelengths, probing the coal dust and gas that serve as the raw material for star formation. Radio telescopes are being built to detect the 21-centimeter signal from neutral hydrogen, which would provide a direct map of the reionization process as it unfolded across cosmic time. And the next generation of space telescopes, including the Roman Space Telescope, scheduled for launch in the mid-2020s, will survey much larger areas of sky at infrared wavelengths, complementing the deep but narrow field of view of James Webb. The Roman Space Telescope is particularly relevant to the story we are telling. While James Webb excels at studying individual distant galaxies in extraordinary detail, its field of view is relatively small. It looks at the universe through a soda straw, seeing a tiny patch of sky in great depth. Roman will see a much larger area, roughly 100 times the field of view of James Webb, though with somewhat less sensitivity. This wide view will allow Roman to conduct surveys of the early galaxy population that are statistically much more powerful than anything James Webb can achieve alone. By counting millions of galaxies across a wide range of redshifts, Roman will provide the definitive census of the early galaxy population that is needed to test the cosmological models. The combination of James Webb for depth and Roman for breadth represents the most powerful observational strategy ever assembled for studying the early universe. Together, they will provide the data needed to determine whether the anomalies discovered by James Webb are the tip of the iceberg or the exception to the rule. Are the oversized early galaxies a common feature of the young universe? Or are they rare outliers in a population that otherwise matches our expectations? The answer to this question will determine the magnitude of the revisions needed to our cosmological models. Let us now turn to one of the most fascinating theoretical implications of the James Webb discoveries: the question of whether the age of the universe itself might be wrong. The age of the universe, 13.8 billion years, is not a directly measured quantity. It is derived from a combination of observations and a cosmological model. The primary observational constraint comes from the cosmic microwave background, specifically from the detailed measurements made by the Planck satellite. By analyzing the patterns of temperature fluctuations in the cosmic microwave background and fitting them with the lambda, CDM model scientists can determine the parameters that define the expansion history of the universe. From those parameters, they can calculate how long the universe has been expanding, which gives the age. But the accuracy of this age depends on the accuracy of the model. If lambda CDM is not the correct description of the universe, or if the model is missing some important piece of physics, then the derived age could be wrong. And the James Webb observations are among the most significant challenges that lambda CDM has ever faced. Some theorists have proposed that the universe might be older than 13.8 billion years. If there is some mechanism that caused the expansion rate to slow down at early times and then speed up, or if the transition between matter domination and dark energy domination happened differently than lambda CDM predicts, then the universe could be older without contradicting the cosmic microwave background data. An older universe would provide more time for the formation of massive galaxies and supermassive black holes, alleviating some of the tension between observations and models. One specific proposal along these lines comes from a theoretical framework called tired light cosmology, though this is generally not taken seriously by mainstream physicists because it conflicts with too many other observations. A more respectable variant involves modifications to dark energy. If dark energy is not a constant as assumed in lambda CDM, but instead varies over time, then the expansion history of the universe could be significantly different from what the standard model predicts. Some models of evolving dark energy produce expansion histories that are consistent with the cosmic microwave background data, but result in a universe that is somewhat older than 13.8 billion years. However, changing the age of the universe is not a simple fix. The age is constrained not just by the cosmic microwave background, but also by the ages of the oldest known stars, the abundances of heavy elements in ancient stellar populations, the cooling rates of white dwarf stars and several other independent lines of evidence. All of these converge on an age in the range of 13 to 14 billion years. Making the universe significantly older would require reconciling with all of these independent constraints, which is a formidable challenge. A more nuanced possibility is that the relationship between redshift and time is not quite what we think it is. In the Standard Model, a galaxy at redshift 12 existed about 350 million years after the Big Bang. But if the expansion history is different from what lambda CDM predicts, then the same redshift could correspond to a different age. The galaxy might still exist at redshift 12, but the universe might have been older at that redshift than we currently calculate. This would provide more time for structure formation without changing the total age of the universe. The details of how the expansion history would need to change to solve the early galaxy problem are still being worked out. It is a complex mathematical problem that involves balancing multiple observational constraints simultaneously. The cosmic microwave background, the distribution of galaxies at lower redshifts, the Hubble constant measurements, and now the James Webb early galaxy data all need to be accommodated within a single self-consistent framework. Finding that framework is one of the central challenges of modern cosmology. There is also the question of what these observations mean for the Big Bang theory itself. Some media coverage of the James Webb discoveries has suggested that the telescope has disproved the Big Bang. This is not accurate. The Big Bang theory broadly construed is supported by an overwhelming body of evidence, including the expansion of the universe, the cosmic microwave background, the abundances of light elements, and the observed evolution of structure over cosmic time. Nothing that James Webb has found contradicts any of these fundamental pillars. What the telescope has done is challenge the specific details of how structure formed within the Big Bang framework. It is the details that need revision, not the framework itself. The distinction between the framework and the details is important. The Big Bang tells us that the universe began in a hot, dense state and has been expanding and cooling ever since. Lambda CDM tells us the specific way in which that expansion and cooling proceeded and how structure formed along the way. The James Webb observations are challenging Lambda CDM, not the Big Bang. It is like saying that a particular recipe for chocolate cake did not come out right. The problem is with the recipe, not with the concept of baking. That said, the revisions to Lambda CDM that may be needed could be significant. If the cold dark matter component of the model needs to be modified, if the expansion history needs to be revised, if the models of star formation and black hole growth need major overhauls, then the resulting framework could look quite different from the one we have today, even while still being recognizable as a Big Bang cosmology. Science does not typically make sharp breaks with the past. It evolves. The heliocentric model of the solar system did not abolish astronomy. Einstein's relativity did not abolish Newtonian physics. It extended and refined it. Similarly, whatever emerges from the James Webb era will not abolish the Big Bang. It will extend and refine our understanding of what happened after it. Let us consider now the human side of this scientific revolution. Because the James Webb discoveries are not just changing our understanding of the cosmos, they are changing the lives and careers of the scientists who are working with the data. The James Webb Space Telescope has been described as a generational instrument, meaning it defines the scientific landscape for an entire generation of astronomers. The graduate students and postdoctoral researchers who are analyzing the first James Webb data are the scientists who will build the next generation of cosmological models. The questions they are asking, now the anomalies. They are investigating the theories they are developing will shape the field for the next 20 to 30 years. this is an extraordinary time to be entering the field of astronomy. The data is fresh, the models are in flux, and there are genuine mysteries waiting to be solved. The speed at which results have been published in the James Webb era is unprecedented. In previous generations of astronomy, major discoveries took years to analyze and publish. The James Webb data has generated a flood of preprints and papers, many appearing within weeks or months of the observations being taken. This rapid publication rate has created a dynamic and sometimes chaotic environment where results are debated, revised, and refined in near real time. It is science at its most alive, with competing teams publishing conflicting analyses, challenging each other's methods, and driving the field forward through vigorous but constructive disagreement. Some of the most productive debates have centered on the interpretation of photometric versus spectroscopic data. As we discussed earlier, many of the initial claims about extreme high redshift galaxies were based on photometric estimates that were later revised by spectroscopic follow-up. This process of initial excitement followed by careful verification is normal in science, but it has played out at an accelerated pace in the James Webb era. The result is a literature that is both extraordinarily rich and sometimes confusing, with earlier papers presenting results that have been superseded by later analyses. Navigating this literature requires careful attention to the dates of publication and the methods used, a challenge that is familiar to scientists, but that can be bewildering to outsiders trying to follow the story. The international character of the James Webb mission has also been a notable feature of the early results. Teams from dozens of countries have contributed to the analysis of the data, bringing different perspectives, different analytical methods, and different theoretical frameworks to bear on the same observations. This diversity of approaches is a strength. When multiple independent teams analyze the same data using different methods and arrive at similar conclusions, the confidence in those conclusions is greatly strengthened. And when they arrive at different conclusions, the disagreements point to the areas where more work is needed. The story of James Webb's early galaxy discoveries is still being written. The telescope is expected to operate for at least 20 years, far longer than its minimum design life of 5 years. Over those 2 decades, it will continue to probe the early universe-gathering data that will gradually resolve the current anomalies and likely uncover new ones. The picture of the cosmic dawn that emerges from this sustained campaign of observation will be far more detailed and nuanced than anything we have today, and it will almost certainly contain surprises that we cannot yet imagine. One of the most important upcoming observing programs involves ultra-deep surveys that will push James Webb to its absolute limits of sensitivity. By pointing the telescope at a single patch of sky for hundreds of hours, astronomers can detect galaxies that are far too faint to appear in the shorter surveys conducted so far. These ultra-deep observations will probe the faintest and most distant galaxies in the universe, potentially detecting the very first stellar systems that formed during the Dark Ages. If those first systems can be identified and characterized, they will provide direct constraints on the initial conditions of galaxy formation and the physics of the first stars. Another important future direction involves the study of the intergalactic medium at high redshifts. The intergalactic medium is the sparse gas that fills the space between galaxies. By studying how the light from distant galaxies is absorbed as it passes through the intergalactic medium, astronomers can measure the neutral hydrogen content of the universe at different times and map the progress of reionization. James Webb is uniquely suited for this work because its infrared sensitivity allows it to observe the absorption features in the spectra of galaxies at the highest redshifts, where the relevant wavelengths have been shifted beyond the range of ground-based telescopes. The quest to understand the early universe is not just a scientific project. It is a human project. It reflects our deepest desire to understand where we came from and how the cosmos that produced us came to be. The James Webb Space Telescope is the most powerful tool we have ever built for answering these questions. And the answers it is providing, while unexpected and sometimes unsettling, are bringing us closer than ever to understanding the true story of cosmic dawn. Let us now explore what the James Webb discoveries tell us about the nature of time and distance in the universe, because the concepts of time and distance in cosmology are not as straightforward as they are in everyday life. And the early galaxy observations are forcing us to confront some of the most counterintuitive aspects of how the universe works. When we say that a galaxy is 13 billion light years away, what do we actually mean? In everyday language, a light year is the distance that light travels in 1 year, roughly 9.5 trillion kilometers. So 13 billion light years sounds like a straightforward distance, but in an expanding universe, the concept of distance is more complicated than that. The light from a galaxy at redshift 12 was emitted roughly 13.4 billion years ago. During the time that light was traveling toward us, the universe was expanding. The galaxy that emitted the light has been moving away from us the entire time. By the time the light reaches our telescopes, the galaxy is much further away than 13.4 billion light years. In fact, using the standard lambda CDM model, the current distance to a galaxy at redshift 12 is roughly 33 billion light years. The galaxy is more than twice as far away as the time it took the light to reach us would suggest. This seems paradoxical. How can something be 33 billion light years away in a universe that is only 13.8 billion years old? The answer is that the speed of light limit applies to objects moving through space. It does not apply to the expansion of space itself. Space can expand at any rate, and the objects embedded in it are carried along with the expansion. A galaxy that was relatively close to us when it emitted its light 13.4 billion years ago has been carried away by the expansion of space to a current distance of 33 billion light years. Neither the galaxy nor the light broke any speed limits. The space between us simply grew. This distinction between the light travel distance and the proper distance has important implications for how we interpret the James Webb observations. When we say that James Webb is looking back 13.4 billion years, we are describing the light travel time. The light took 13.4 billion years to reach us, but the actual distance to the object as measured at the present moment is much greater. And the actual distance the light traveled is neither of these numbers, because the space through which the light was traveling was itself changing size during the journey. The mathematical framework for handling these distances is provided by general relativity, Einstein's theory of gravity, and the geometry of space-time. In general relativity, space and time are not separate entities. They are woven together into a four-dimensional fabric called spacetime. The presence of matter and energy curves this fabric, and the curvature determines how objects move and how light propagates. The expansion of the universe is described by a mathematical quantity called the scale factor, which describes how the distances between objects change over time. All the different notions of distance light travel, distance proper distance, angular, diameter, distance luminosity, distance are derived from the scale factor and its evolution over time. For the purposes of interpreting the James Webb data, the most important thing is the relationship between redshift and the age of the universe at the time the light was emitted. This is called the look-back time. A galaxy at redshift 12 has a look-back time of approximately 13.45 billion years, meaning the light was emitted 13.45 billion. years ago when the universe was about 350 million years old. A galaxy at redshift 14 has a look-back time of approximately 13.51 billion years when the universe was about 290 million years old. The differences in look-back time at these extreme redshifts are small, just tens of millions of years, because the universe was expanding very rapidly at that early epoch, and a large change in redshift corresponds to a relatively small change in time. This compression of time at high redshifts is one of the reasons why the early galaxy problem is so acute. The difference between a redshift of 10 and a redshift of 14 corresponds to a time interval of only about 190 million years. Yet within that interval, we are seeing galaxies that range from moderately massive to extremely massive. The timeline is so compressed that even small differences in the onset or rate of star formation can have dramatic effects on the properties of the galaxies we observe. To illustrate this, consider two galaxies. Galaxy A starts forming stars 300 million years after the Big Bang. Galaxy B starts forming stars 400 million years after the Big Bang. If we observe both galaxies at a look-back time of 500 million years after the Big Bang, Galaxy A has had 200 million years to form stars, while Galaxy B has had only 100 million years. Galaxy A has had twice as long to build up stellar mass. In a linear model of star formation, Galaxy A would be roughly twice as massive as Galaxy B. But in reality, star formation is not linear. It is governed by complex feedback processes, gas dynamics, and gravitational interactions that can produce exponential growth under the right conditions. A galaxy that got a 100 million year head start might be not just twice as massive, but 10 or 100 times more massive, depending on the details. This sensitivity to initial conditions is one of the reasons why the early galaxy population is so diverse. Small differences in the formation time, the initial gas density, the dark matter halo mass, and the local environment can lead to dramatically different outcomes within the compressed timeline of the early universe. Two galaxies that appear side by side in the James Webb images might have very different histories and very different futures despite being observed at essentially the same cosmic epoch. The nature of time in the early universe also raises philosophical questions about what it means to observe the past. When we look at a galaxy at redshift 14, we are not seeing the galaxy as it exists now. We are seeing it as it existed 13.5 billion years ago. The light has been traveling for almost the entire history of the universe. By the time we see it, the galaxy has continued to evolve for 13.5 billion years. It has merged with other galaxies, formed new generations of stars, possibly been consumed by a larger structure. The galaxy we see in the James Webb image no longer exists in the form we are observing. It is a ghost, a snapshot of a moment that is impossibly distant in both space and time. And yet that ghost tells us something real about the universe. It tells us what conditions were like 13.5 billion years ago. It tells us what was possible in a universe that was only a few 100 million years old. It provides data that constrains our models and tests our theories. The fact that we can see into the past by looking into the distance is one of the most remarkable properties of light and one of the most powerful tools in all of science. This ability to see the past is not unique to astronomy. In a very real sense, we always see the past. The light from the sun takes about 8 minutes to reach Earth, so we always see the sun as it was 8 minutes ago. The light from the nearest star, Proxima Centauri, takes about 4.2 years to reach us. But these timescales are negligible compared to the look-back times involved in observing the early universe. When we look at a galaxy at redshift 14, we are looking back in time by 13.5 billion years. we are seeing the universe in its infancy, and the information encoded in that ancient light is telling us that the infant universe was more precocious than we ever imagined. Let us now address one more important aspect of the James Webb story: the question of what these discoveries mean for the search for extraterrestrial life. At first glance, the connection between early galaxies and the search for life might not be obvious. Early galaxies are vast cosmic structures containing billions of stars, while the search for life focuses on individual planets orbiting individual stars. But the two topics are connected at a deep level, because the early galaxies set the stage for everything that came after, including the formation of the planets and environments where life might develop. The heavy elements that are essential for life, carbon, nitrogen, oxygen, phosphorus, and many others, were produced inside stars and scattered into space when those stars died. The first generations of stars produced the first heavy elements. The galaxies that hosted those stars were the factories where the raw materials of life were first manufactured. By showing that these factories were operating earlier and more efficiently than we expected, James Webb is telling us that the chemical prerequisites for life were established earlier in cosmic history than we previously thought. If heavy elements were being produced as early as 300 to 400 million years after the Big Bang, then the first rocky planets could have formed very early as well. A rocky planet requires elements like silicon, iron, magnesium, and oxygen, all of which are produced in massive stars and dispersed by supernovae. If galaxies were already chemically enriched at these early times, then the first rocky planets might have formed billions of years earlier than the Earth, which formed only about 4.5 billion years ago. Consider the implications of this timeline. The Earth is roughly 4.5 billion years old. Life on Earth appears to have originated within the first billion years of the planet's existence, possibly much sooner. The oldest confirmed evidence of life on Earth dates to roughly 3.5 billion years ago, and some contested evidence pushes that date back to 4.1 billion years ago or earlier. If rocky planets in other galaxies formed as early as 12 or 13 billion years ago, and if life could arise on those planets with the same speed it arose on Earth, then there could be civilizations in the universe that are 8 or 9 billion years older than ours. The mind struggles to comprehend what a civilization with that much of a head start might look like. 8 billion years of evolution and development. 8 billion years of potential technological advancement. The numbers are staggering, and they remind us that the James Webb observations are not just about galaxies and black holes. They are about the conditions that set the stage for everything that followed, including the possibility of life far more ancient than our own. This has implications for the question of when and where life might have first arisen in the universe. If rocky planets existed in the first billion years of cosmic history, and if those planets had liquid water and a source of energy, then life could potentially have arisen very early. The universe might have been teeming with microbial life long before our own planet even existed. This is a speculative idea, and there are many reasons to be cautious about it, not least the fact that the early universe was a much harsher environment than the present-day cosmos, with higher levels of radiation and more frequent catastrophic events. But the James Webb data has moved the goalposts. The chemical conditions for life were established earlier than we thought, and the clock for the origin of life may have started ticking billions of years before Earth formed. This connection between early galaxy evolution and the origin of life is one of the reasons why the study of the early universe is not just an academic exercise. It has implications for our place in the cosmos. If the universe produced the ingredients for life very early, and if those ingredients were distributed across many galaxies and many environments, then the probability of life existing elsewhere increases significantly. We are not just studying distant galaxies. We are studying the environments that set the stage for our own existence and potentially for the existence of life forms that we have not yet discovered. The story of the early universe, as revealed by James Webb, is a story about origins. The origin of the first light, the origin of the first structures, the origin of the elements that make up planets and living things, and ultimately, the origin of the conditions that made our own existence possible. By looking back in time 13.5 billion years, we are not just observing the distant past. We are tracing the chain of events that led to us. Every atom in your body was once inside a star. Every star was once inside a galaxy. And every galaxy was once a tiny fluctuation in the density of the primordial universe, a barely perceptible ripple in the fabric of reality that gravity amplified over billions of years into the structures we see today. James Webb is showing us the earliest chapters of that story, the chapters where the ripples first began to grow, where the first stars ignited in the darkness, where the first galaxies assembled themselves from clouds of hydrogen and helium and began the long process of chemical enrichment that would eventually produce planets, oceans, and living things. These are the chapters that we knew the least about before James Webb launched, and they are the chapters that are now being rewritten in light of the telescope's extraordinary observations. There is a beautiful irony in the story of the James Webb Space Telescope and its early galaxy discoveries. The telescope was designed to answer a specific set of questions about the early universe. Scientists had predictions about what it would find. They expected to see the first faint protogalaxies slowly assembling in the dark. They expected to map the process of reionization as it unfolded across cosmic time. They expected to test the lambda CDM model by observing the universe at the highest possible redshifts. And in a sense, the telescope is doing exactly what it was designed to do. It is observing the early universe with unprecedented clarity and testing our models against reality. But the answers it is providing are not the ones anyone expected. Instead of confirming the standard picture of slow hierarchical galaxy assembly, James Webb has revealed a universe that was far more dynamic and far more productive than anyone imagined. Instead of finding faint protogalaxies at the edge of detectability, it has found bright massive systems that challenge the fundamental parameters of our cosmological models. The telescope is answering the questions it was designed to answer. It is just that the answers are different from what the designers anticipated. This is the essence of scientific exploration. You build the best instruments you can. You point them at the most promising targets. You collect the data with as much precision and care as possible. And then you let the data tell you what the universe is actually doing, even if it contradicts everything you thought you knew. The willingness to be wrong, to revise, to start over with a better model is what separates science from dogma. And the James Webb era is providing one of the most dramatic demonstrations of this principle in the history of astronomy. Let us consider the broader historical context of this moment. Humanity has been observing the sky for thousands of years. The ancient Babylonians tracked the motions of the planets. The Greeks developed geometric models of the cosmos. The Islamic astronomers preserved and extended classical knowledge during the medieval period. Galileo turned his telescope toward Jupiter in 1610 and saw its moons, providing the first telescopic evidence that not everything in the heavens orbits the Earth. Each generation of astronomers has built on the work of the previous one, using better instruments to see further and more clearly. The invention of the reflecting telescope in the 17th century, the development of photography in the 19th century, the construction of the great mountaintop observatories in the 20th century, the launch of the Hubble Space Telescope in 1990. Each advance in technology has brought with it new discoveries and new questions, and each set of new questions has driven the development of the next generation of instruments. James Webb represents the latest and most powerful step in this centuries-long progression. It is the culmination of everything we have learned about optics materials, science cryogenics, rocket engineering, and infrared detection. It embodies the collective knowledge and ambition of thousands of scientists and engineers from 3 space agencies and more than a dozen countries. And the fact that it is producing discoveries that challenge our existing models is not a sign that something has gone wrong. It is a sign that the instrument is working exactly as intended, probing regions of the universe that we have never been able to study before and finding things that we did not expect. The emotional impact of the James Webb discoveries on the scientific community has been profound. For decades, cosmology has been in what some have called a precision era, where the fundamental parameters of the universe were being measured with increasing accuracy, and the basic framework of lambda CDM was being confirmed and refined by successive observations. There was a sense in some quarters that the major questions had been answered, and that the remaining work was largely a matter of filling in details. The James Webb observations have shattered that sense of completion. The early galaxy anomalies have reintroduced genuine uncertainty into cosmology. Scientists who spent their careers refining the standard model are now confronting the possibility that significant revisions are needed. Young researchers are entering a field where the foundations are in flux and the biggest questions are genuinely open. The result is an intellectual energy and excitement that has not been felt in cosmology for years. The field is alive again in a way that it has not been since the discovery of dark energy in 1998. Some senior astronomers have described the experience of working with James Webb data as reminiscent of the early days of the Hubble Space Telescope, when every new observation seemed to reveal something unexpected. The sense of discovery that permeates the field right now is palpable at conferences and in research group meetings. Arguments about the interpretation of data are passionate and productive. Collaborations are forming between theorists and observers who might not have worked together before. And the papers being published are not just incremental refinements of existing knowledge. They are genuine explorations of new territory grappling with observations that do not fit neatly into any existing framework. The public fascination with the James Webb discoveries has also been extraordinary. The first deep field images released in July 2022 were viewed by hundreds of millions of people around the world. The beautiful, detailed images of galaxies, nebulae, and star-forming regions captured the imagination of people who might never have thought about cosmology before. And the scientific story behind those images, the story of a universe that grew up too fast, and a set of models that cannot explain what the telescope is seeing, has added an element of mystery that makes the mission even more compelling to the general public. People are drawn to unsolved puzzles, and the puzzle of the early galaxies is one of the most captivating unsolved puzzles in science. This renewed vitality is already producing results. Theoretical papers proposing new models of early galaxy formation appear almost daily. Observational teams are conducting follow-up studies to confirm or deny the most extreme claims. New analytical techniques are being developed to extract more information from the James Webb data. And plans for the next generation of observatories are being influenced by the questions that James Webb has raised. The telescope has not just changed what we know, it has changed what we are trying to find out. One of the most important intellectual shifts driven by the James Webb discoveries is a renewed appreciation for the complexity of the early universe. For a long time, the standard model of cosmology provided a reassuringly simple picture. The early universe was hot and homogeneous. Structure formed gradually through gravitational instability. Galaxies assembled hierarchically from smaller building blocks. This picture was elegant and it fit the data available at the time. But James Webb has shown that the real early universe was much more complex, much more diverse, and much more surprising than this simple picture suggested. The complexity of the early universe is now one of the central themes of observational cosmology. How did so many different types of objects, massive galaxies, compact red sources, active black holes, chemically enriched systems emerge so quickly from the relatively simple initial conditions of the Big Bang? What processes allowed the universe to develop such diversity in such a short time? And are the mechanisms that drove early cosmic evolution fundamentally different from those that operate in the present-day universe? Or are they the same mechanisms operating under different conditions? These are deep questions, and they will take years, possibly decades, to fully answer. But the fact that we can now ask them with specificity backed by real data from the real early universe is itself a remarkable achievement. A generation ago, these questions would have been purely theoretical. Today, they are empirical. We have images and spectra of the objects that embody these puzzles. We can measure their properties, count their numbers, and compare them directly to the predictions of our models. The early universe is no longer a blank page. It is a page filled with text that we are only just beginning to read. As we look ahead, several key questions will define the next phase of James Webb science. First, what is the true abundance of massive galaxies in the early universe? Current surveys have covered only a tiny fraction of the sky, and the statistics are still limited. Larger surveys in the coming years will provide much more robust counts of early galaxies, allowing us to determine whether the anomalies are widespread or confined to particular regions. Second, what are the detailed physical properties of the earliest galaxies? The initial observations have provided measurements of brightness color and rough estimates of stellar mass. But detailed studies of individual galaxies, including their gas content, their star formation rates, their chemical compositions, and their internal dynamics are still in the early stages. These detailed studies will reveal the physical mechanisms that allowed some galaxies to grow so quickly, and will test the various theoretical explanations that have been proposed. Third, how did supermassive black holes form and grow in the early universe? The discovery of massive black holes at high redshifts is one of the most challenging puzzles raised by James Webb. Future observations will characterize these black holes in greater detail, measuring their masses, their accretion rates, and their relationship to their host galaxies. This data will help discriminate between different models of black hole seed formation and growth. Fourth, when and how did reionization occur? James Webb is providing the first detailed measurements of the galaxy population during the epoch of reionization. As these measurements are expanded and refined, they will reveal the timeline and topology of reionization with unprecedented clarity. Understanding how the universe transitioned from neutral to ionized is critical for connecting the observations of the very early universe to the conditions that prevailed at later times. And fifth, what new physics, if any, is needed to explain the James Webb observations? This is the deepest and most far-reaching question of all. If the anomalies cannot be explained by adjusting the parameters of existing models, then new physics may be required. This could involve modifications to dark matter, dark energy inflation, or even gravity itself. The stakes are enormous because any change to the fundamental physics of the universe would ripple through every subfield of physics and astronomy. The answers to these questions will not come all at once. They will emerge gradually over the next decade as James Webb continues to collect data and as new observatories come online to complement its capabilities. The process will involve moments of breakthrough and moments of confusion, as is always the case in science. But the direction is clear. We are moving toward a deeper and more complete understanding of how the universe grew up. And the picture that emerges will be richer, stranger, and more beautiful than anything we had imagined before James Webb opened its golden eyes to the cosmos. The universe grew up fast, faster than our models said it could, faster than our theories predicted. Somewhere in the darkness between the Big Bang and the modern-day cosmos, something happened that turned the simplest possible beginning into a riot of complexity and structure in what was by cosmic standards the blink of an eye. We do not yet fully understand what that something was, but for the first time in history, we have the tools to find out. 13.8 billion years ago, the universe was born. It was hot. It was simple. It was uniform. And within a few 100 million years, an eye blink in cosmic time, it had produced massive galaxies, supermassive black holes, heavy elements, organized structures, and possibly the first conditions under which life could begin. The speed of this transformation is one of the great surprises of modern science. It tells us that the universe is more creative, more energetic, and more surprising than we ever gave it credit for. And we are only just beginning to understand how it happened. The James Webb Space Telescope is our window into that understanding. A golden mirror floating in the darkness 1.5 million kilometers from home, collecting ancient photons that have been traveling since before our planet existed. Those photons carry the story of the cosmic dawn, a dawn that came faster and brighter and stranger than anyone expected. A dawn that is still unfolding in the data, streaming back from the most remote outpost of human engineering. The universe grew up fast, and we are finally starting to understand why. Not because we have all the answers, but because for the first time we have the right questions, the right tools, and the right resolve to chase those questions into the deepest reaches of space and time. The story of cosmic dawn is the story of everything. It is the story of how the nothing became the something, how the simple became the complex, how the darkness became the light, and it is still being told, one photon at a time, one galaxy at a time, one discovery at a time. The mirror is listening, the universe is speaking, and the words it is whispering are more extraordinary than anything we dared to imagine.